Today I'll be talking about some new progress on separating the complexity classes QMA from QCMA with the classical oracle. Let's first recall the classical complexity classes NP and the closely related class MA. Here we have a prover that takes as input an instance X and sends a proof pi to the verifier, who then accepts or rejects. The case of NP corresponds to deterministic verifiers, and the case of MA corresponds to probabilistic verifiers. Here, P is computationally unbounded. We say that an instance is in the language if the verifier accepts with probability 2/3, and we say that the verifier is not in the language if no matter what pi is produced, the verifier rejects except with probability 1/3. And just note that these 1/3 and 2/3 thresholds are arbitrary as long as they are non-negligibly separated. So now the question is, what happens when we move to the quantum setting? Well, one option for generalizing NP is the notion of QCMA, where the proof pi remains classical, but now the verifier V is allowed to be a quantum algorithm. We could have instead defined the class QMA, where both the verifier and the proof are actually quantum. So a central question in quantum complexity theory is whether QMA and QCMA are the same or are they different? In other words, do quantum witnesses give more power? Unfortunately, separating QMA from QCMA is beyond the abilities of current complexity theoretic techniques. And so we typically, in such a case, move to oracle separations. Oracle separations don't necessarily imply that the actual complexity classes are different, but they might be some indication. So the first result along these lines was due to Aronson and Kuperberg, who gave a quantum oracle, U, such that QCMA is not equal to QMA. So what about a classical oracle separation? Quantum oracle separations are largely considered non-standard by the community, and so an open question since their work was whether there was a classical oracle O, accessible in superposition, such that QCMA and QMA are separated relative to this classical oracle. There have been a number of partial results over the years, from simple candidates with no formal justification to various works that place some sort of limitation on the way the verifier can access the oracle, but actually prove a separation. However, to date, there has been no work that actually separates these unconditionally relative to a classical oracle accessible in the standard format. And the major challenge is that the prior oracles for separating QMA and QCMA are highly structured, and these highly structured oracles don't seem to be amenable to known query complexity techniques. In this work, we don't solve the problem, but we make something that might be considered progress towards answering this. And what we do is we give a new candidate oracle separation that in some intuitive sense uses less structure. And in particular, we show a conditional separation. Namely, we show that under a certain statistical conjecture that has no obvious connection to quantum, that there exists a classical oracle O separating these classes. So this means that we've reduced the problem of separating QCMA and QMA relative to a classical oracle to solving a particular statistical conjecture we make. All right, let's jump into our oracle. So let's start with the yes instances. Here, we imagine choosing a large, random, but sparse subset of the overall domain, which we'll call N. We'll then choose a random state psi with support on S. Psi is down here on the bottom left. And in the Fourier domain, by applying the quantum Fourier transform, we get the state psi hat, which is on the bottom right. And we notice that the psi hat, actually, the amplitudes don't concentrate around their mean. And what this means is we can choose a random set U that is in some way biased toward the high amplitudes of psi hat. And the result is that we can choose U so that U is roughly 1/2 of N, half of the entire domain, but 3/4 of the mass of psi hat actually lies on U. So our oracle is going to be S together with this U. Now, what do our no oracles look like? Well, informally, our oracles are going to be S set to a tiny but superpolynomial size subset of N, so much smaller than S in our yes instances. And U is going to be a random set that intuitively is unrelated to the set S. And it's straightforward to show that our oracles are actually in QMA. The idea is as follows. For a yes instance, our witness state is just going to be psi. And here's our verifier. First, it checks that S accepts psi, which for the valid witness state will happen with probability 1. Then it computes psi hat by taking the Q of t, and checks that U accepts psi hat. Now here, because we chose U such that 3/4 of the mass of psi hat is in U, the overall verifier will actually accept with probability roughly 3/4. On the other hand, for a no instance, we can show that because S is extremely small and U is somewhat unrelated to S, that actually no matter what witness state you produce, the acceptance probability is very close to a half. And so we get a separation between no and yes instances, and therefore this places the language in QMA. The much harder question is to prove QCMA hardness. And here's going to be our approach. Our goal is to consider a supposed QCMA verifier, V bar, that accepts any yes instance SU. And what this means is that for any oracles S and U, there exists a classical witness of polynomial size W, such that the verifier accepts W with probability at least 2/3. Now what we want to do is modify S and U into a no instance S prime U prime, such that it fools this verifier. In other words, that the verifier, when given oracle access to S prime and U prime and given the witness W, outputs 1 with probability pretty close to the case where it was given the yes instance, and in particular it'll be pretty close to 2/3, and therefore the verifier does not correctly reject S prime U prime. So let's build up to the overall proof. We're going to start with a very simple case where there's no W or U, and the verifier just has access to S or S prime. Well, here we can actually let S prime just be the empty set. And the idea is that, let's suppose toward contradiction that the verifier on the empty set S prime actually had a significantly smaller acceptance probability than when given S. What this means by standard quantum query complexity techniques is that V bar to the S must actually place significant query weight on S. In other words, a significant fraction of the weight that V is querying to S must actually be in the set S. So what we can do is we can then measure a random query that V makes to S, and with decent probability we'll actually get a point in S. So we have an oracle then that makes queries to the sparse set S, a small number of queries, and produces an element in S. This is actually known to be hard. This contradicts the known hardness of Grover search. So in this case, where the verifier doesn't have access to W or U, we're happy. Okay, let's make things a little harder. Let's just say there's no U, but now the verifier actually gets a witness W. The challenge is that W may actually encode points in S because W can depend arbitrarily on the set S. So we can't anymore set S prime to be the empty set. So here's what we're going to do. We're going to imagine running V bar, making queries to S on the witness W, and we're going to let T be the set of heavy queries. Here a heavy query is just a point where when we look at the query to S, that point has a significant amplitude. Since the verifier has to be efficient, we know that the total amplitude across all queries is only polynomial, which means that the number of heavy queries can't be too big. So what we're going to do now is we're going to let S prime be the intersection of T and S. So it's the set of points in S such that their query weight under V bar is heavy. The point is that S and S prime only disagree on very light queries of V bar. So now suppose to our contradiction that V bar, when making queries to S prime, accepts with probability noticeably less than V bar making queries to S. This means V bar must place significant query weight on the difference between S and S prime, and since S prime is a subset of S, this just means it places significant query weight on the points in S that are not in S prime. So what we're going to do now is we're going to measure a random query of V bar making queries to S. And what this results in is that it will actually produce a point in S minus S bar in proportion to the query weight. But since points in S minus S bar are all light queries, the query weights are negligibly small. And this means that the points sampled through this process have high entropy. So what we'll do is we will just repeat this many times. Since the witness W is classical, this is totally fine. We can run V bar of the S, evaluate on W many times, measure random query each time. And by the lightness, these points that we sample will have high entropy and therefore will be distinct with high probability. And as a result, we can generate as many points as we want in the set S. So the consequence of this is that under the assumption that that S prime is accepted with probability noticeably less than S, we can actually get an algorithm that outputs elements in S in polynomial time, and it can output as many elements in S as we would like. So the next step is that the algorithm above requires this witness that depends on the set S, and we're going to remove that witness. So what we're going to do is we're going to just generate the witness at random. And we will set L to be much larger than the size of the witness. And the result is that we get an algorithm that outputs L elements in S. The probability is no longer high, but the probability is just the probability that the witness was correct. So the probability is 1 over this 2 to the length of the witness, but we're outputting L elements in S where L is much longer than the length of the witness. And it turns out that this actually contradicts known query complexity results, in particular this result of Hamoudi and Magnia's, that show that to output elements of S, you can't do better than probability 2 to the minus L. And this is a contradiction because we set L to be much larger than the length of the witness, and therefore our algorithm actually succeeds with too high a probability. And this means that our original assumption that there was a significant difference in acceptance probability between V bar making queries to S prime and S, that assumption is false, and therefore we have shown that the acceptance probabilities are similar. Okay, so now we need to move on to the general case, where V bar actually gets queries to both S and U. So we can go through the stuff on the previous slide, and what we get is an algorithm that makes queries to S and U and outputs a bunch of elements in S with probability 2 to the minus length of witness. However, this U is correlated to S, and as such, we can't just apply the existing results to get a contradiction. This U may reveal points in S and may actually facilitate A outputting elements in S without reaching a contradiction. So our goal is going to be to somehow try to nevertheless show that even with access to U, such an algorithm is a contradiction. So let's first consider an easy case where U is k-wise independent for some super polynomial k. And what I mean by k-wise independent is that it's k-wise independent even conditioned on S. Now, a result from a few years ago says that k-wise independent functions are actually perfectly indistinguishable from truly random functions as long as your number of queries is at most half of k. And since k is super polynomial, this means that a k-wise independent function is actually indistinguishable from a random function to any polynomial time adversary. And this is enough to get our contradiction because we can simulate U using a random function independent of S, and we can actually simulate U efficiently on the fly. And the result is that we actually get an algorithm, A to the S, that outputs L elements in S with too high a probability and contradicts the previous results. And I'm going to generalize a little bit to something I call nearly k-wise independent. First, let's define U to be, quote, nearly k-wise independent if there exists some correlated oracle V such that V is exactly k-wise independent, and also for all x, the probability that x is in the symmetric difference of V and U is negligible. So in other words, for every point, the most certainly U and V will agree on that point, but there may be some negligible chance where U and V will differ. And there's a straightforward theorem using known query complexity techniques that says that if U is nearly k-wise independent, then it is actually indistinguishable from truly k-wise independent of up to k over 2 quantum queries. So we just introduced a new notion of being close to k-wise independent, but it's actually not the usual notion of almost k-wise independence that is commonly used in the literature. So the notion of almost k-wise independence says that the k-wise marginals are statistically close. It turns out that for classical query algorithms, this is actually enough to show indistinguishability from truly random functions. However, quantumly, you can actually construct counterexamples to show that almost k-wise independence is not enough. But the good news is that we show that nearly k-wise independence is enough quantumly. So this might position nearly k-wise independence as a useful concept for arguing query complexity results. Now, where does our U fit in? Unfortunately, we don't get exact k-wise independence. This is what motivated us to consider other notions of approximate k-wise independence. But we do get something pretty strong. So for all sets T of size at most k, we can actually show that the probability that T is contained in U is very close to 2 to the minus size of T. In particular, it's at least 2 to the size of minus T, and at most a very small multiplicative factor greater than 2 to the minus size of T. And compare this constraint that we get for our particular U to the case of exactly k-wise independent functions, which is equivalent to saying that for all sets T, the probability that T in U is 2 to the minus T. So we've relaxed from the exact case 2 to the minus T to being very close to 2 to the minus T. And in particular, our bound on how close this can be to 2 to the minus T is much tighter than you would get in the typical notions of almost k-wise independence. And so this leads to the statistical conjecture we make, which asks that which asks the following: for all sets T of size at most k, if the probability that T is contained in U is very tightly constrained relative to 2 to the minus size of T, the conjecture states that this condition is enough to actually conclude that U is nearly k prime wise independent for some large k prime. K prime might be different than k, might be the same, but for some large k prime, we want that U is nearly k prime wise independent. So this conjecture just basically is the bridge that we need to connect the statistical property we can actually prove on U to this notion of nearly k-wise independence that is sufficient to get our proof to go through. And so based on everything we've seen, together with this conjecture, we can conclude that that our language is not in QCMA, and therefore we have our oracle separation between QMA and QCMA. So the obvious open question is whether this conjecture is true or false. It could be true, could be false. We don't really know. If it does happen to be false, there is still the chance that our oracles could give a separation, but we might need to adjust the proof strategy to do so. And that completes my talk. Thank you.